So the basic idea of digital modulation is that instead of using an analog time-varying envelope, we simply use a binary change of state. And so here's an example of amplitude shift key where we have one amplitude and then we have another amplitude. And we do this in discrete steps. And part of the reason to do this is that digital modulation can be more immune to noise. And the way to think about it is if I just have two different amplitudes, all I need to do is tell the difference between those two. I don't have to follow the fine variations of an analog one. So this would help if the variation in this envelope had some noise on it and this had some noise on it. As long as the separation was large enough, I could detect the two signals. So there's a couple different types of modulation, and all through this we're going to be using a terminology called shift keying. And I'm not sure the historical origin of this, but I imagine it may go back to Morse code where you keyed in the code. And shift is just referring to what it is that we're changing. So on this top one here, it's a binary phase shift keying. And it's pretty easy to see that a 1 is this phase and a 0 is a different phase. So all we're doing is changing phase as we move between 1 and a 0, meaning that 1 is a specific phase and 0 is another specific phase. We could also have binary amplitude shift key, which is like what we saw before. We have two different envelope amplitudes. One represents a 1, one represents a 0. And then of course we can have a binary frequency shift keying where we change a frequency between two. So in all of these you'll see this PSK, ASK, FSK. You'll just kind of see this terminology of something shift keying referring to what kind of modulation. Basically, as we talked in the modulation module, we discussed that you can modulate the amplitude, the phase, and the frequency, and so this gives you three different knobs to turn in a digital fashion. So I want to talk a little bit about the concept of a signal constellation. And we have two signals on the left here. One is A cosine omega t right here, and we have B cosine omega t. And maybe what we're going to do is we're going to go shift between A and B to represent, maybe this represents a 1 and this represents a 0. Well, it's going to be convenient if we do this graphically, and what we're going to do is we're going to take an axis, which I'm just going to call the cosine omega ct axis here, and this is basically showing that I've got one amplitude here and I've got the other amplitude here, and the constellation is basically going to go back and forth between these two. In this example it was cosine omega t. Often we'll just call this the in phase component. And this will make a little bit more sense as we look at variations other than amplitude, because we can look at variations that might be caused by phase. And so here's an example where we have A cosine omega t and B cosine omega t, but we've changed the phase by 90 degrees. And so now we've basically moved up 90 degrees, and the amplitudes, if you look at this, is still different. So we can have this change between two amplitudes, and we can also have a change between two phases. So the way to look at this is you could actually, what I've drawn here is 4 different points, and we can actually continue this so that we represent signals on an in phase and a quadrature diagram. And so what we do is we plot basically the amplitudes and the phases of each signal that represents a piece of data. So in this example, this might represent 0 and this might represent 1. However, as we'll see going down, this could maybe be 0, 1, 1, or 0, 1, 0, and this could be 0, 1, 1. Each one of these points represents a state, and we can have a number of states. We can have 2, 4, 8, 16, as many states, frankly, as you want. And we'll see more of that as we go along. So let's look at an example. So this is binary phase shift key. So we saw this before. This is where we have 0 and 180. And we can represent this on the in phase axis as just a +1 and a -1. And so as we transmit back and forth, we just go back between these two dots. Another one is called QPSK, which is for quadrature phase shift key. And you can see quadrature means I've got 4 different phases. And you can see here explicitly what I mean. Because there's 4 phases, I can represent 4 different binary numbers. Each one of these represents a point. So here we are with 180 degrees. Here we are with 0 degrees. Here we are with 90. And here we are with 270. And you notice the amplitude's not changing. I'm just changing the phase as I move between these different constellations. And this introduces subtly a concept of the fact that one physical state can represent many bits. Okay? We'll talk a little bit later, but we're going to call these symbols. So these are symbols, and they can represent a multi-bit state. Okay, and we'll talk more about that, but the basic idea is each one of these dots represents a piece of information. So this graph says that we can transmit 4 different pieces of information with one carrier frequency. Now, if we go back and we look at binary phase shift key, we can write it mathematically like the following. And what we have here, this is a string of square waves, and then it's going to be multiplied by a cosine of omega ct. Now, we've put in the phase in here, but if we choose the phase to be 0 or pi, we could just rewrite this signal like this. And the way we can think about this is this. The AK pi is my digital signal, 0101, and cosine is my carrier. And you can see here I've got my, let me erase that. I've got my change here, and then I've got, looks like it stays the same, and then another change there as we move along. And so here's our input information, and here is our cosine there. And so mathematically we represent it this way, and it's kind of convenient. If you want to know what this pi function looks like, it looks like this. It basically represents the minimum width of our pulse, and then we're just going to put on ones and zeros. So here we have a 1, here we have a 0, here we have a 1, here we have a 1, here we have a 0, and so forth. And so we represent our digital data as a series of unit parts of time where we assign them either a 1 or a 0. And as I said before, you can tell right here we've just got 2 bits of data. We've got 2 different states. We've got a one phase, and then we've got the other phase. And this leads us into this idea we've been talking about symbols. So this is actually an easy concept, but it gets complicated because down the road you're going to be hearing symbol bits, symbol bits, symbol bits, and it's going to be a little bit confusing, the difference between the two. And if you get them straight early on, it's pretty easy for you to be able to handle this. So the idea is that k bits can represent 2 to the k symbols. All right. And so the way to think about it is if I've just got 0 and 1, right, I have 2 symbols, -1 and 1. But if I've got 2 bits, meaning I can have 0, 0, 0, 1, 1, 0, 1, 1, I can represent this as 4 different symbols, right? And then I can go and I can say, well, if I've got 3 bits, I can do this with 8 symbols. And so the symbol represents the collection of bits that we are going to need. And so when we looked at our constellation where we have our I and our Q, each dot represents a symbol. It represents a collection of bits. And the reason why this distinction is important is we're going to transmit symbols in our digital radios, And each symbol can contain multiple bits. And so the idea is, I'll just show it examples here. Here's where we had, this is 0 degrees and this is 180 degrees, right? And this is 90 degrees and 270, right? That means I can be coming along and suddenly shift phase, and I go from here to here. This might have been a 0, 0, and this might be 1, 0. So by doing one change in the physical domain from one symbol to the next, I've actually changed from those 2 bits to these 2 bits. And so it's a way for us to basically encode additional information by just sending one physical state and understanding that it can represent multiple bits. And we'll go over this in more detail, but this idea of symbols and bits is a very important one.